Welcome learners. In today's lecture, we are going to look into an important aspect of vector algebra, and that involves multiplication of two vectors, also known as vector multiplication. And in this category, we are going to talk about two of the multiplication techniques known as a dot product and a cross product. So we are going to see how we can take two vectors and find out the dot and cross product between them to locate a point in free space. So before we look into the official definitions of these two terminologies, let us first understand the concept behind vector multiplication, starting first with the dot product. So dot product is also known as a scalar quantity because its output is always scalar. Similarly, in the next few seconds, we are going to learn about cross product as well, which gives the output in a vector form. So let us first discuss the dot product. So what is a dot product? So the idea is, if we have any vector, let's say vector A, and we have another vector B, and there is a certain angle made between these two vectors. So dot product basically tells us that what's the relationship between vector A and B. So we write it as, if we have vector A and we apply the dot between A and B, so what's the relationship between these two vectors? So mathematically it is, you take the absolute of vector A, you take the absolute of vector B, or you take the magnitude of vector A and magnitude of vector B, and you find the angle between them, which is a cos theta identity. So this is how we apply the formula to find the dot product between two vectors. Putting it in simple terms, dot product basically tells us what is the projection of one vector onto the other. In this case, what is the projection of vector A onto vector B? And we can say that this portion till here is what the vector A is projecting itself with a certain angle of cos theta. So this is, in simple words, what the dot product suggests. It also means how much two vectors are matched to each other, or what are the characteristics of the vectors or the two vectors. So this is where the dot product comes. Whenever we want to see how much is the effect of one vector onto the other, or how much similar these vectors are, we take the assistance of dot product, and mathematically the angle between them is calculated using the right hand rule. So you might have studied, if you have a right angle triangle, so we can find the angle of that 90-degree triangle by looking at hypotenuse, the opposite side, and the adjacent to it, and the cos theta is selected because of the trigonometric ratios based on the mnemonics of. So this is the mnemonic which basically tells us where the sine or cos or tangent theta can be used in a 90-degree triangle or a right angle triangle. This you might have studied in your lower classes, but for our case we are not concerned on this. Rather, we want to utilize this tool to locate a point in free space with the help of two vectors. So if we put an official definition to it, so dot product is basically used, so we can say dot product is used to multiply a given vector, or specifically a given vector field. So we have already understood what is a vector field in our previous lectures. So we basically multiply a given vector field by the component of another vector, by the component of another field or another vector. So here this is an important term, component of another vector. So we'll come back to this shortly. So it is used to multiply a given vector field with the component of another vector that is almost parallel to it, that is parallel to the first one or the original vector. So this is the official definition of a dot product. And what's the angle that can exist between the dot product? Obviously it is going to be between 0 and 180 degree. So the cos theta will normally be in this range in terms of its degree variable. So this is what the dot product is all about. And what other properties we see from the dot product? So if we look at the official definition which we have just written, so dot product between two vectors is vector A and vector B can be in n-dimensional space, but we are just restricting ourselves to 3D space in this course of EMT. So mathematically it is basically the modulus of first vector with the modulus of second vector and the cos of angle between two vectors. Some of the properties associated with dot product is that it is a commutative property, that if you multiply two vectors in one orientation, the result will be the same if you change the orientation of the vectors. It is distributive over vector addition, so if you take the product of a multiplication vector in parenthesis, you can use it as a dot b plus a dot c. And important thing with dot product is that if you have two vectors which are mutually orthogonal, so we have talked about this term as well, mutually orthogonal, or they are perpendicular to each other, or we can say if they are 90 degree apart, then their product will be a zero value, which means if I have a vector in this direction, let's say vector A, and the other vector B is in the opposite direction and the angle between them is 90 degree, so their dot product A dot B will always be 0. And why is that? Because we are using cos of 90 degree in this expression, and cos of 90 is basically 0. So this is an important term to remember whenever we are dealing with the dot product of two vectors and the angle between them is 90 degree, we immediately say that the dot products are orthogonal vectors. And again, going back to our previous discussion in the previous lecture where we talked about the rectangular coordinate system and its unit vectors. So you remember we wrote something like, if unit vector ax is dot product or multiplied with the same vector, its value becomes 1, and if we multiply the dot product of one unit vector with another vector, it becomes 0. And this is the main reason behind it, because the angle is cos of 0, which is 1, and for this case it is cos 90. So that's why the unit vectors are also going to be utilizing the dot and later on the cross product between coordinate systems. So this is the reason behind it. So coming back to our understanding of dot product, we look at some of the operational definitions that are associated with dot product, and this is very useful especially for this chapter where we are going to utilize certain numericals to find the solutions of these vectors. So these are known as operational definitions for the dot product. And what are those points? So most of the points you are familiar about. The first point being, okay, whenever we have a single vector and you want to take a dot product with the same vector, its output becomes absolute square. So this is the first thing that we have. So again, this is a scalar quantity, it's a scalar magnitude. So dot product of a vector with itself will give you the absolute square of it. Second property, we just saw that if we have unit vectors x, y and z in the rectangular coordinate system, so if you have a unit vector of the same orientation, its output will be 1, and if you have the dot product with a 90 degree axis, its dot product will be 0. Again, we discussed about this shortly. The third postulate is, if we have a vector A with its components as ax, ay and az, and we have another vector B with its components bx, by and bz, so the dot product between A and B, so vector A and B, so basically we are talking about the left hand side of the basic equation for dot product. If I call this equation A, it is going to be, you take the vectors ax and bx, you multiply them together, So basically you multiply the same variables and you multiply it with ax dot ax, plus you take the common vectors of ay and by again with dot product of ay to ay, plus you take it as a z to b of z with product of a z to a z. So finally the output comes out to be, you have ax bx plus ay by plus az into bz. So this is the dot product's result, and you can see this is a scalar quantity. So it means that the output of two vectors being multiplied in terms of the dot product will be a scalar output. And why these unit vectors have disappeared? Because they all equate to 1, as cos of 0 is 1. So this is the third postulate and an important one that we are going to be utilizing when solving numericals related to dot products. The fourth postulate is a straightforward. If you want to find the angle between two vectors, so we stick to the basic equation, the basic equation being equation A. So you can generate angle from here. So let me write the equation again. So the dot product of two vectors is the magnitude of two vectors being multiplied and the cos of angle between them. So the angle between them is equal to cos of inverse A dot B divided by magnitude of A dot magnitude of B. So this is how we find the angle between two vectors. And finally, if you want to find the component of a vector in a given direction, so there are two ways to solve it. One is called, so we know what are the components of any vector. It's a scalar and a vector component. So if it's a scalar component, how we are going to find it? So we are going to find it, for example, if I have a vector b and I have a vector a being of the longer magnitude compared to b. So if I want to find the dot product between these two vectors, the definition says it is the multiplication of one vector field with the component of another vector field. So this means that the component of vector a is its unit vector a of a, let's say. So this is the unit vector, or we can also put it as a of x, because if it is on the x-axis. So this is the component of the next vector. So in the definition, when I highlighted this portion, component of a vector, it meant this thing, that we are going to take one vector and multiply it with the component of the other vector, as we saw here with vector b and a. So the scalar component is then written as b dot a. So let's say if we have vector a and vector b, then its output is going to be magnitude of vector b multiplied with cos of theta between them. Now where is the second term? It should have been vector a as well, but since we are taking the component of vector a, which is a unit vector with the magnitude of 1, so this gets disappeared and its value is 1. So this is how the component or a scalar component of a vector is calculated in dot product. Similarly, if we want to find the vector component of it, so the straightforward method is that we keep the answer which we got from the above scalar component and we just multiply it with the unit vector, in this case unit vector a of x. This gives us the vector projection or vector component of the dot product. So these are the 5 postulates that we are going to use heavily in solving problems related to dot product. So again, the physical interpretation of a scalar and vector project is shown that if we have vector a and it is being projected on a longer vector b, so this is the length of the vector a that is projecting its shadow onto vector b. Now if you want to find the component, we want to find how much projection a is happening on b, so basically we take the component of vector b and then we do the multiplication. So the scalar projection is, we take the magnitude of a and b, we take the dot product and divide it by the absolute or the magnitude of b. Similarly, if you want to convert this scalar projection into vector, so the equation remains the same, we just introduce the vector element, in this case a unit vector, along the b vector. This gives us the complete vector projection onto a. So this is how the physical interpretation is for the component of a vector. In order to further understand this concept, let us look at an example and see how we can go about this. So let us read the question. The question says that the vector field which is provided to us is represented as G, and we have been given a point Q. So the things that we need to find is what is G at Q. So what is the G at Q? This is the first thing we need to find. The second is what is the scalar component of G at Q in the direction of AN, and the third is what is the vector component of G at Q in the direction of AN, and finally what is the angle between G and A of n. So these are the four things that we need to solve. So let us start by first figuring out what is G at Q. So this means we need to write G in terms of the position vector Q. So if we draw this to visualize it, it should be something like this. So this is y, this is x, and this is z. So we have 4 points on x, so 1 2 3 4, so it will be something like this. Then we have 5 points on y, 1 2 3 4 5, so this is the fifth point that we have over here. So this is the cross section, and if we draw it like this, and on z we have 2 points, so the 2 points will be something like this. So this is the point Q that is in space, having value of 4, 5 and 2. Okay, so now what is G at Q, which means we are going to replace incorporate the value. So the value of G is around AX minus 2.5 x A of y and plus 3 A of z. So G at point Q, the vector form, is going to be, what is y? So y is 5, so I'll put 5 for the unit vector A of x minus 2.5 into 4, so it is going to be 10 around AY unit vector, plus we don't have any z, so it will remain 3 of AZ. So this is the value of G at position vector Q. Now the next thing we want to find is the scalar component. So let's go with the scalar component. So we have seen, in order to find the scalar component, what we want to do is we go back to the original equation. So if this is the equation, this one, equation A, so we know we need to do the dot product of A with the second component of a vector. So in this example, the vector is G and we want to do the cross product with A of n, or sorry, the dot product with A of n. So it comes out to be G, we are going to take G at R of Q. So let me say G at Q. So it is going to be 5A of x minus 10A of y plus 3A of z, and you take the dot product with what is the value of A of n? This is the value of A of n. So it is going to be 1 by 3 2A of x plus A of y minus 2A of z. So how do we take the dot product? We are going to segregate x, ax, ay and az. So if I take 1 by 3 as common, and I can say 5 multiplied by 2 for A of x, plus I will take minus 10 multiplied with 1 for the AY unit vector, plus I am going to take 3 multiplied with minus 2 or around A of z. So it comes out to be 10A of x. So let's take 1 by 3 common for all. 10A of x minus 10A of y. Let's simplify things. Okay, minus 10A of y, and then you have minus 6A of z. So this is what I am having, but remember that A of x is getting multiplied with the A of x over here. So as we remember, this should be AX multiplied with AX, this should be AY with AY and AZ. So all of these dot products of similar units will be equal to 1. So we'll be left with 10 minus 10 and minus 6 and divided by 3. So the final answer comes out to be, this will be cancelled out, minus 2. So this is the scalar output from the scalar component. Next we want to find the vector component. So what we can do is we need to find what is the vector component or the projection of vector A onto B in terms of the vector representation. So we already knew from our previous case that if we have G at Q have a dot vector with A of n, this is the scalar vector which we got as -2. So we just multiply it again with the unit vector direction, which is going to be A of n. This means our answer will be -2, and an was 1 by 3 2a of x minus a of y minus 2a of z. So once you solve this, it comes out to be, you do the multiplication and it will be minus 1.33a of x, then you have minus 0.667a of y, and you have plus 1.33a of z. So again you can see now the answer has unit vectors in them, thus saying that this output is a vector form answer or a vector component representation. Final part of the question is to find the angle between g of a. So the angle is basically cos inverse g with a of n vector divided by the absolute of g of n, g of a with g of n. But we know from our understanding that one of the element is a unit vector, so this will become equal to 1. So our answer will be, or our equation will be simplified to g of a of n equals to absolute of g cos of theta. So this is the basic equation that we have utilized, but the second component is a unit vector, so the answer will be g of a of n is -2, the scalar component. Magnitude of g of n means we basically take the square of the value of g, which we got as 5 square, the first value g at q, 5 square plus 10 square plus 3 square. So this comes out to be, and then we have cos theta, so we can't forget about cos theta of a. So it comes out to be, let me use the calculator. So this is 25 plus 100, and it is 134 cos of theta. So we are interested in finding the theta, which is equal to cos inverse -2 divided by under root 134, and it comes out to be 99.9 degree. So this is the solution to this example, where we have figured out the dot product between two vectors in terms of its scalar component, vector component, and the angle between them. So this is the example. Okay, now let us come to the second quantity, and that is the cross product. So now in vector multiplication, we are now moving into the second kind of multiplication, and that is a cross product, which is basically we have two vectors a and b, and the thing in vector product is, or cross product, is that both of these angles should be 90 degree apart. And to differentiate from the dot product multiplication, we apply an x sign over here, and the output of this will also be a vector quantity, not compared to a scalar of the dot product. So if we have cross product, normally we multiply two vectors which are 90 degree apart, and the output is also a vector product which is 90 degree compared to the first two elements. So we have definition over here that as the vector c is perpendicular to both vectors a and b, vector c being the resultant vector, and the direction is given by the right hand rule, and that can also perform as a parallelogram of that vector. So mathematically, cross product is represented as this, where the angle is now sine theta, and you have a unit vector which is normal to the original vector. So normal being they are 90 degree apart to the original unit vectors, let's say a n and b n. So this is the cross product. So you can imagine a cross product if you are trying to insert a screw into some wooden piece, and if you move from a to b, so the screw will be rotated like this, which means the direction of a cross b is inward. If you move from b to a, this means you are unscrewing, so it will be negative a cross b. So this is the orientation of the cross product. Properties of the cross product is that it is anti-commutative, so A cross B equals to minus B cross A, and distributive property remains the same, that A cross B plus C is equal to A cross B plus A cross C. So these are the properties that we normally utilize with the cross product. Here you can see in the right hand rule how these cross product behave. So if I am moving from A to B, I am going in the upward direction. This is another analogy that when you can use. If you are moving from B to A, it can be negative B to A. And in the right hand rule, our thumb, so let's say our index finger points to a vector A, our middle finger points to a vector B, and the angle between these two are 90 degree. The resultant vector is the thumb A cross B, which is again 90 to A and B. So these are all mutually orthogonal to each other. Similarly, this analogy can be applied to a parallelogram where we have vector A, another vector B, which is 90 degree apart, and the output will be A cross B, which is again 90 degree from the other two vectors A and B. So this is the cross product, and again in this we multiply a vector, and the definition remains the same, that we multiply a vector field to the component of another field, but the main thing is that all vectors are perpendicular to each other. Okay, so another thing associated with cross product is what is going to happen in terms of its unit vector. So if we have a unit vector in the RCS system, this is y, this is x, this is z. So if the unit vectors are moving in the anti-clockwise direction, the unit vectors being ax, ay and az, so if we move in this direction, it will always give you output as 1. But if you have the same vectors, ax multiplied by ax or ay cross product with the same vector, or az with the cross product same, the output will be 0. Why? Because now the equation has a sine theta, so sine 0 is 0 and sine 90 is equal to 1. So that's why if we have the same elements, the output or the product will be 0, and if you have different values, the output will be a certain value. It is not going to be 1, but it will be the next value. For example, if I have ax multiplied with ay, so the output will be az. If we have ay cross product with az, output will be a of x. If I have az cross product with a of x, so if I have az, sorry about that. So if I have az with a of x, the output will be a of y. So these are the cross product orientations that we need to keep in mind whenever we are solving questions related to cross product. So now let us have a look at an example and see how the cross product is figured out. So if we are given any vector a, we can write it into scalar and vector components. Same with vector b. So normally we take the cross product of two vectors like we take the determinant of a vector. So we basically sum the elements together. So if we have a cross b, you can see if I want to find a of x as a common factor, so I am going to multiply ay with b of z and az with b of y, and so on and so forth. So our basic equation comes out to be this. Let's put this through, understand this through an example rather than using the representation or mathematical representation. For example, I want to find or I have been given a vector a and its value is 2ax minus 3ay plus a of z, and I have been given another vector b. So again I'll put the arrowheads so it is known that it is a vector, minus 4a of x minus 2a of y plus 5a of z, and I need to find what's the cross product between vector a and b. So in order to find the cross product, we first prepare a matrix with unit vectors ax, ay and az, and then we add the scalar components of a and b into this. So we will write ax, AY, AZ, and then we will take BX, BY and BZ. This means our matrix will be AX, AY, AZ, and the values will be 2, minus 3, 1, minus 4, minus 2 and 5. So this is how we formulate the matrix. Then we are going to solve for A cross B as such that first we consider unit vector A of X and then we write its respective values. So in order to do that, let me change the color of this discussion. So if I want to find A of X, we basically make an imaginary T on this. So we close the vertical and horizontal bars. So we are left with these things as a cross product between them. So the value in the bracket comes out to be A of Y multiplied with B of Z minus A of Z multiplied with B of Y. So this is the value we get for A of X, plus we move to A of Y, and now this comes out to be, so we write the value. Now for A of Y, let me again change the color. So for A of Y, we are going to make the T shape such that these vertical components are blocked for A of Y. So we are left with A of X with B of Z minus A of Z with B of X. So let's put it like this. So we get a plus for the third element A of Z. What do we get? Again, let me change the pointer so that the things become, let's go this one. So now for A of Z, we take the vertical axis of A of Z and the horizontal row for A of Z. So we are left with A of X multiplied with B of Y minus A of Y multiplied with B of X. So our values now, if we input everything into the values, so A of X will now have a value of, so A of Y is minus 3 into B of Z 5, then you have minus 1 with minus 2 plus A of Y comes out to be 2 into 5, and you have minus 1 into minus 4, and then plus A of Z comes out to be 2 into minus 2 minus minus 3 into minus 4. So now final answer comes out to be minus 13A of X plus 14A of Y minus 16A of Z. So this is the cross product between two vectors A and B, and I do suggest that you verify the multiplication and the answer and to confirm whether I got the correct positive and negative signs or not. But this is how you solve a problem related to the cross product of two vectors. So this was all about the vector multiplication in terms of dot and cross product. The remaining content we will have a look at it in the next lecture.